Good morning, everyone, and welcome once again to another JKMRC Friday seminar series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we would like to acknowledge the traditional owners and custodians on the land on which we meet today. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections with country, and we recognize their valuable contributions to Australian and global society. It is my great pleasure today to welcome Professor Simon Michaux. Simon has an applied science bachelor's degree in physics and geology and a PhD in mining engineering from the University of Queensland. He has 18 years of work experience in the Australian mining industry in research and development, 12 months at Ausenco in the private sector, and 3 months in Belgium at the University of Liege, researching circular economy and industrial recycling. Currently, he's working at GTK in Finland, where he's involved in minerals intelligence, minerals processing, and geometallurgy. His long-term objectives include the development and transformation of the circular economy into a more practical system for the industrial ecosystem to navigate the twin challenges of the scarcity of technology minerals and the transitioning away from fossil fuels. Today, his talk will be about the purple transition, the start of a possible solution. Please join me in welcoming Simon.
Okay. Can you hear me okay?
Big thanks, Simon.
All right. So I'm going to present today the start of the solution set. Work thus far has been looking at the problem of the green transition, how it won't work, but now I'm starting to look at solutions. Okay, in summary, the first 10 slides or so are going to be a quick summary of where we're at with regard to the work around the green transition won't work in its current form. So what might? I'm proposing the purple transition. There's a reimagined commodities sector, which takes the form of what I call the resource balanced economy. This is what the circular economy should become. And around it, you've got 4 foundation technologies: liquid fuel fission using thorium as the fuel, combustion of iron powder, ammonia fueled internal combustion engines, and battery chemistries that are not lithium based. 3 are in commercial development at the moment. And the technology presented here is decades old. There is no one magic technology that fixes all our problems. It is a magic source is how these are stitched together and how they support each other in a network. Right, so the basic question was this: will this work for everyone the way we hope? And how do we continue to resource this? So the work done there is based on a couple of maps. Here's the first one. What were the physical tasks done in the calendar year of 2018? What was the true scope of useful work done? And if that work was done by non-fossil fuel systems, what would they be? Where each class was represented by a commercially available unit. Sum it all together and calculate the quantity of electrical power needed. And then given an energy mix proposed by the IEA in 2050, excuse me, how many new power stations will we need? The elephant in the room, and I didn't really understand it at the time when I found this, was wind and solar are highly intermittent, and wind and solar are supposed to be the primary energy source of power systems post-fossil fuel as proposed. They're highly intermittent and they need a buffer, so to make sure that the power systems are stable and produce the same power in the same form. The size of that buffer has proven to be quite a contentious issue. I've got some information today to present to give support of the idea that the buffer is actually much larger than we think it is. So the global system was 1.4 billion vehicles traveled an estimated 16 trillion kilometers in the calendar year of 2018. So to do this, to actually sort of do this phase out fossil fuels, we need an additional 48,939 terawatt hours. And we need about 800,000 new power stations of average size. Now, put this in context, in 2018, that was the amount of power that we consumed. So we need to bring in a system more than twice the size of the one we've got at the moment. And the power plant fleet has got to be more than 10 times the size of what it is at the moment. And that's the numbers projected into the split proposed by the IEA. The buffer is associated with wind and solar only, but in practical terms, the rest of the grid will need some kind of buffer. All right, so now that we know how much extra power that we've got, well, the questions became how many physical units we'll need to fill the system, how much steel, hydrogen, and ammonia production would be needed annually, and what's the metal content of each unit, wind turbines, solar panels, and batteries. What battery capacity needs to be operating? Now, the battery capacity of the electric vehicle fleet was 65 terawatt hours. Now, all of the studies that I've seen in this area were talking about a battery capacity in gigawatt hours. One of us is badly wrong, and I suspect all of the studies have vastly underestimated the size of the global transport fleet. So also the size of the battery capacity for the electric vehicle fleet is about 65 terawatt hours, but we could need several thousand terawatt hours in battery capacity for storage buffer. So that means if we use the entire electric vehicle fleet as a buffer storage, it still would not be enough. Not even close to being enough to actually sort of mitigate the size needed for power storage. So what's the market share of the different chemistries? Another IEA prediction. And what's the metal content in each battery chemistry? And that gave us the total quantity of metals needed and in what kind. So now that we know the number of metals, where do we get it from? So can recycling deliver it, this amount of metal? And it turns out the answer is no. We'll come back to that in a moment. Can the existing mining industry in its current form deliver this metal? I use 2019 because it's the last year for the COVID supply chain disruptions, which we had some very strange data artifacts after 2019. So can mining production in its current form deliver? Then can the mining industry expand quickly? And so what's in the mineral reserve portfolio? Will that be enough? And so what about long-range capacity, where we're looking at things like conventional resources? And work done by Harold Sverdrup has actually sort of done some geostatistics of resources of that and done Hubbard curve peaks on each metal. And would it help if we mined the sea floor as underwater resources? And the simple answer to all that is no. And then we're back to, should we consider developing a fundamentally different plan? And I'm going to talk to you today about that. So size of the buffer. This is some data that was actually pointed to me from the US Department of Energy, which I then followed up on. In the United States, there is a really, really large power grid called PJM-RTO. It serves 100 million people. And in that power grid, it's got wind and solar capacity. The data for 2022 for wind and solar, and later 2023, show that wind and solar underperform for months of the year. It's about 6 months for solar, and it was about 4 months for wind when they were below par. In 2023, we saw the same pattern. Now, what's interesting is when it goes below par, it stays below par for a period of time. And so if we were to take that information and if we were to say, well, what is the actual, if we were to set that power grid to run at a particular capacity for what it could handle, and in this case, it was 22% for solar, and I think it was 24% for wind. Right, and so what we found for solar in 2023, to actually sort of the amount of power that would have to be in storage to keep that standard capacity, we needed 23 days of storage. We also needed that storage to be accessible and deliverable across a 212-day sequence. Right, and so that's the information that's new. You had to keep it for such a long time. Wind only needed 6 to 8 days. and it needed to be kept for 122 days. Now, what there's a study done by Ranu and Quist that actually suggested we need 12 weeks buffer, and that is to allow the grid to recover from a string of bad weather, where you've got patches of bad weather a couple of days long, but then you've got 5 or 6 patches separated by only a few days. The grid never gets a chance to recover. So what you're looking at here is a power grid buffer that needs to be 23 days long, kept for 212 days, and then the grid needs to recover after that. So this is the idea that it's empirical evidence to show the size of the grid is of the order of, of 20 days plus. Like, 28 days is not unreasonable. Right. So all of those was, the study was split into 4 basic buffer sizes. So you had the entire system with a buffer. Conventional thinking believes it only needs 5 to 7 hours. So that's the pink in what's got a 6-hour buffer. And then there were 3 other stages based with a reference. The most sensible answer is probably between the red and the blue. So for each metal, for each unit, everything was then added up and then summed together, and that gave us the amount of quantity of metal for each in terms of a quantity. What is in this list? Well, 1.39 billion electric vehicles, 65 terawatt hours of batteries for the EVs, 29 million hydrogen fuel cells, about 38 billion, that's with a B, solar panels, 1.3 million wind turbines of 6.6 megawatt capacity. Stationary power storage across the 4 scenarios. We're going to build some more nuclear power stations, hydropower stations, geothermal, and bio-waste to expand the system. Put this up against global mining production in 2019, and we can start to see some comparisons. So let's take out copper. So we've got all these different metals. So instead of actually bombarding it with every metal, let's look at just copper. Right. So in 2019, the market produced 24.2 million tons of copper across the year. If we were to do a 6-hour buffer, we'd need about a little bit less than 12 years of production. We could probably manage that if that was the answer. But once we actually sort of get out to 28 days, now we're at 254 years. Or at 12 weeks, now it's 745 years. So to hit these targets, the mining industry would have to expand greatly. So the problem is we need to get this done in the next 25.5 years. It's actually less than that now. It's a little bit more than 25 years to get it done by 2050, and the practical answer's there somewhere. So the mining industry in its current form needs to expand. Then there's the question of recycling. So everything we've used in the last, say, 30 years has been used and then thrown away in a rubbish heap somewhere. So between 1990 and 2023, that's 34 years, I got what was the mining production of each of these metals. So across those 34 years, we mined 520 million tons of copper. Okay, the multiplier is the amount of copper that we would need to hit these targets, split up by different buffers. So if the answer is between the red and the blue, it's between 11 and 34 times the historical capacity, the quantity that was actually mined. So if we were to go out to all the rubbish dumps, dig up all the rubbish, find the copper, all of it, recycle it, get 100% recovery, would that copper be enough? Not even close. Now, all of these metals have the same basic profile. That's copper. So recycling can't deliver this, is the answer. And this is a mining story. So there's nickel, lithium, cobalt, graphite, vanadium. 453 times the mining rate of the last 34 years, right, is what we need to hit this target. So the expansion we're talking about is enormous. It's not an efficiency step change. of a couple of percent here and there, it's a massive increase. The basic outcome is what has not yet been mined cannot be recycled. There's just not enough metal in the system. So then there was to actually look at what if we were to sum together mineral reserves, mineral resources, and undersea resources. So all the metal that we know of in the system we call planet Earth, up against the amount of metal that we need to replace the existing system as it was in 2018. And so this is a log scale, and that's that same data on a linear scale. So remember, this is just for the first generation of technology, and things like an electric vehicle will last at best 20 years. A wind turbine will last about 20 years. The economic efficiency of these units is close to 7 or 8. But let's say 20 years is the number. In 20 years' time, we have to do it all again. And that'll put pressure on recycling. If we were to actually get that amount of metal from somewhere, we'd then have to recycle it. And our current capacity is nowhere near able to do that. So the solution, the answer, the outcome was mining existing mineral reserves, resources, recycling. None of that will be enough to manufacture the first generation of renewable technology. And there's a black swan at the very heart of the energy planning for the future, for the green transition. This work has been put into a peer-reviewed journal, and a couple of weeks ago, it finally passed after 2.5 years of review. So it's in the final stages of being formatted now, and its release is imminent. But it's now coming. It is now in a peer-reviewed journal, the full calculation, all 298 pages. The basic conclusion is this: the green transition will not work. We have to go back to the drawing board and do something else. So what's happening? Well, fossil fuels are being phased out. The green transition faces serious resource supply bottlenecks, but even if we were to do it successfully, well, we've got to, the renewable technology may not be strong enough and effective enough to replace fossil fuel capability. So what might work? And this is what I'm calling the purple transition. Why purple? It's my wife's favorite color. Ha ha ha. All right, what are we trying to do? We want electricity generation. We want transport. We want manufacture. We want to be reliable and consistent power generation, stable in all weathers and all geographic locations, preferably in a concentrated form to support industrial actions. And we want a low materials footprint. And each unit has a long working life. And once each unit is taken offline, it is designed to be recycled. Not the case at the moment. Oh, and we also want a minimal waste plume with a very low environmental impact. So this is the laundry list. I now think that we can deliver at least most of this in some form, whereas before that wasn't the case. Driving questions to answer are as follows. What minerals do we need? Why do we need them? In what quantities? Where do we get them from? Once we have them, how do we manage them responsibly? What should our energy systems be? And how should we change our, how should we change our industry to develop a more responsible relationship with the planetary environment? So the conventional answer to these questions is the green transition and the circular economy. However, in response to that, the work done over the last couple of years, the green transition could transform into the purple transition. Develop a proposed system of energy generation and transport that does, let me download that. Go away. Right. That does not produce carbon pollution and does not need vast amounts of exotic materials. The circular economy could evolve into the resource balanced economy. Develop a resource management system that accounts for embodied energy of all actions and can holistically manage system limitations more effectively. Quick word on the circular economy. In its current form, it's not thermodynamically balanced. This is what we think the circular economy is when we discuss it. So we've got industrial manufacture, consumption, waste management, and recycling, and the assumption is all material flows between them is equal. What really happens is this. So we want to make things, industrial manufacture. We source our materials, usually metals, from an external source. That's what we call mining. There's a waste plume of both mining and the industrial manufacture. Then that goes on to materials consumption. That assumption is subject to market forces and growth. Then we have waste management. A lot of that goes into landfill. There are difficulties of collecting waste of all products that can be recycled, and so a lot of it's lost. What does make it to recycling? Well, we only recycle a few elements out and the rest is thrown away. We take what is valuable. So the vast majority of the material that we produce is in the end thrown away, even with a recycling angle. And then what comes out of the recycling is then inserted into industrial manufacture. Right, so stream B is subject to growth-based economics. And due to technological advancement, what we consume is always, what we manufacture is always the next generation. There's always a new iPhone coming out, and it has different materials in it. So C and A are of different character. And so what ends up going into stream D is so much smaller than stream C because we're just not collecting very much. So by the time we get to A, stream A is nowhere near enough to actually serve our manufacturing needs. At the heart of all of it, there's energy. So this is actually what really happens. And so the circular economy needs to honor all this in some form. And in its current form, it is thermodynamically imbalanced. The community sector has been misunderstood. When we hear about the 6 o'clock news, we hear about the stock market. Whereas what really happens is a system of between 4 elements. We've got the raw materials, let's call them minerals. There was the technology to extract that raw materials and the energy involved to do it, and the technology involved to turn those raw materials into something useful. Then you've got the economics. You've actually got, where you see one, you've actually got the other 3, and they cannot be separated, not if you do it properly. Now there's the understanding that all 4 of these systems are actually harvesting stuff out of the planetary environment. This is how the system really is, and any new system will have to honor this structure. Now, our relationship between all 4 aspects and the planetary environment is changing. So the resource balanced economy is a system that does these things: resource accounting, management of dynamic equilibrium. For example, let's say we've got a forest. There's trees in the forest that grow over time. How many trees can we cut down to keep up with forest growth so the forest stays a resource in a sustainable fashion? Strategic design, where things are designed to be recycled and they're designed for long-term targets. At the moment, neither happens. Statistical entropy coupled with material flow analysis of each resource. This is a very jargony term, but what I'm really doing here is mapping complexity. How complex is a material flow system? I'm trying to put an energy term to everything. So there's energy, the exergy term, and an emergy term for all physical actions. So we can start actually sort of assembling the metrics for deciding whether something is sensible to do or even possible. Biophysical signatures in what society actually does. Technology application, where old technology drops out and new technology is brought in. What's proposed here is a change in how we design our technology and how we manage our waste streams, and that changes what raw materials we need in what form, and the implication is what we call mining will be integrated more effectively into a full value chain system, and it will be valued differently. Okay, so at the heart of everything, we've got a new system of managing our resources. We've got 2 basic wings here: application and then power generation. In the application side, we've got transport. We've got at the moment petroleum, ICE, electricity, and manufacture. On the energy side, we've got oil, gas, and coal, and nuclear. Fossil fuels are going in their place. We want, and we've also got a whole lot of renewable technology energy generation systems. solar and wind is considered the primary system going forward. We're going to have electric vehicles, biofuels, and hydrogen fuel cells. The problem with electric vehicles is the batteries and the materials to make those batteries. That's not going to work in its current form. Biofuels won't work because the planet can only supply a certain amount of biomass, and we can't make the quantities required. Hydrogen has the limitation of we don't have the technology to store such a large amount of energy and transport it in the form of hydrogen. If we can do those things differently, then the hydrogen system would become more viable. So the hydrogen economy is viable on a small scale, but we've got some real challenges to overcome when we actually want to scale it up. So wind and solar, that Achilles heel is the buffer to manage intermittency. That's actually going to be a problem. All the others, hydro, geothermal, and bio-waste, they're all limited by natural things. Like you can only put so many hydro stations on the ground, and any site that is actually would be suitable for a good hydro system, especially a pumped hydro system, already has a unit on it. Geothermal, same thing. There's not that many geothermal deposits around. We are all waiting on a breakthrough in drilling to happen, which we can go deeper. If that happens, then geothermal comes back on the books. Bio-waste has the same problem as biofuels. We can only produce so much biomass. And wave. Wave works, but the maintenance of these units, they don't last very long. The sea tends to destroy them. And it's also when in a job in Hawaii was how many of these things will we need to actually generate the amount of power, and the number is enormous. It's just not effective enough to be the primary energy system. They all have their place, but they're not able to be scaled. What I call conventional nuclear, light water reactors, this system can't expand fast enough to be useful. If we're taking, even if we only took 5 years to build a power plant instead of 25, the system cannot expand fast enough to generate enough electricity fast enough to replace fossil fuels. What is not really talked about, but something we need to look at, is coal is used in manufacture, and heat in particular is used as a to make a solar panel silicon wafer. You've got to heat that metallurgical silicon to 2,200 degrees Celsius. And at the moment, we use coal to do that. So this is an economy of heat. So, okay, what might work? So this is the resource balanced economy at the center. And around that, we've got 4 technologies. Thorium molten salt reactors, ammonia-fueled ICE, combustion of iron powder as a metal fuel, and different battery chemistries, where the key to success is how these systems are stitched together. So let's look at the first one. So thorium. This is a report from the Oakland Ridge Nuclear Laboratory, 1972. It's a status report of this technology. The cliff notes are it works, and they were requesting funding to make a larger system. This was the trial unit that they had in place, and it generated 6,000 hours of power generation without a problem, and they then shut it down and were awaiting funding for the next step. The Chinese actually have a commercial system already running, excuse me, in the Gobi Desert, 2 megawatt hours. And this is it's a small system. It's my understanding that the Chinese are looking at this very, very carefully. And once they actually have done a few trial systems, they're going to mass produce them. So the East economies, the BRICS economies in particular, they're already looking at this and they're out the gates and running. We're about to be left behind. What is molten salt? So the fuel is a fluoride-based salt with thorium in it. Thorium is not radioactive, but if we bombard it with neutrons with, say, a plug, hang on. Why am I? I just need to get my computer. Why am I not? Never mind. Okay, so the salt is liquefied. Some of the thorium is bombarded with neutrons, and some of that thorium then transmutes into an isotope of uranium, U-233. That is very hot. That uranium then melts the salt and it becomes a liquid. That liquid then moves around the circuit and it exchanges heat. That heat is then used to create steam, which turns a turbine, and that generates electricity. The fuel then moves around the deposit, around the power reactor, and it exchanges heat as it goes. Now, you cannot have a meltdown of a unit if the fuel is already molten. Due to a phenomenon called Doppler broadening, if this reaction gets too hot, it cascades over and collapses in on itself. And so all the control systems to keep the reaction within a temperature range, otherwise the reactor shuts down. There's not one but two things that are preventing a Fukushima-like event. What is interesting to me is that fuel can be taken out of the reactor and put in and cleaned while the reactor's running. And that actually changes the logistics of things. So why am I? Hang on, my computer's hung for a moment. Okay, there you are. This is a group in Copenhagen called Copenhagen Atomics. They've actually got a system called the Onion Core. I actually went to their factory and had a look at it. This is their system. So you've got the reactor. One side is actually moderated by heavy water. Go back. And the other side is the heat exchanger. Heat has been exchanged between two fluids to make sure that there is absolutely no radiation coming out of this system. It's a completely sealed system. That is a size of the full-sized unit once they're manufactured. It's about the size of a shipping container and it arrives on a truck. When it's commissioned, they put 50 years of fuel in the system and there's a 5-year maintenance cycle to strip out the corroded parts. Each reactor is planned to produce 100 megawatts of thermal heat or 40 megawatts of electricity. They're modular, so we can stitch them together to hit whatever power capacity is required. The business model for Copenhagen Atomics is not to sell the reactors, but to rent them. And the electricity will be sold at 2 cents a kilowatt hour. 1 gram of thorium or uranium produces 24 megawatts of thermal energy. So a power plant producing 1 gigawatt a year would consume about 800 kilograms of thorium metal in salt form a year. The reactors will be available for commercial operation in 2028, and apparently they are planning to produce one of these reactors a year. Sorry, one reactor a day, sorry. And based on what I saw, it's that each of these things have a complexity of a 3-bedroom kit home. So that actually shouldn't be a problem. Here is what is in the fuel salt. So about half of it is lithium, so fluoride, sorry, and you've got thorium, and you've got a small quantity of lithium-7. And lithium-7 is the important element to actually sort of manage this. This came off a published mass balance that I found. So what's happening here is conventional nuclear power is what's called solid fuel. The pellets are made up of uranium oxide. Most of it is uranium-238. The usable isotope is uranium-235, and that's only about 4% of the fuel rod assembly. Most of the fuel is shielded by the stuff on the outside, so there's a whole lot of fuel that is actually not used. The liquid fuel system is once everything's molten, it moves through the liquid. All parts of the fuel come in contact with all other parts of the fuel. So what this means is there is no shielding and all fuel can actually take part in the reaction without slowing down anything else. So you can have elements in that fuel that take a long time to react and they still don't shield anything. The isotope that actually runs the reaction here is uranium-233, and approximately 96.9% of the fertile fuel is consumed in transmutation. So we're going from 4% to 96%, and that efficiency difference is massive. So what I did was I mapped out a the performance metrics and flows for a light water reactor, an advanced light water reactor called the AP1400. How much uranium was required and to produce the same amount of fuel. And we're going to produce across 1 year a little 11.2 terawatt hours of electricity. How much waste comes from that, and what do we do with that? So of the 36.9 tons of fuel that goes in, 31.5 tons becomes waste that then has to be and split up and used. And so then that was then taken back to, well, how much uranium do we have to mine out of the ground and how much stuff do we have to process? So then that's that flow sheet there for a generation 3+ reactor. This is actually the standard at the moment. I found a publication for a thorium molten salt system that actually ran in research fashion for a number of years. And I scaled that up to actually match the same amount of power electricity, 11.2 terawatt hours of electricity across 1 year. And I went through the same analysis where we are now mining thorium and making thorium fluoride salt fuel, how much waste comes out of that after 1 year of operation. What this was done on the suggestion of the US Department of Energy, where they wanted an analysis and comparison to generate 1 gigawatt of electricity. What is the footprint of these systems? And so I was able to do the following. To generate 1 gigawatt hour of electricity, we can now compare different parts of the value chain. So for uranium, so the MSR system was had a 75% availability. They kept shutting it down for research purposes and doing stuff. I think that there's no reason why they couldn't match the availability of the light water system at 91.5%, but this was actually the published results. So in terms of how much uranium ore we mine, it's either 14.8 tons of uranium ore or 0.089 tons of thorium. This is in terms of mineral processing. What has to be put through a mineral processing plant? You either have to process 28 kilograms of uranium ore or 170 grams of thorium ore in their parallel systems. What I'm showing here is the thorium system is substantially smaller in footprint. In terms of waste produced for the same gigawatt hour of electricity, you've got 2.8 kilograms versus 0.0044 kilograms. And the mass of fuel, reactor fuel, is so much different. This comes back to the uranium system wastes 96% of the solid fuel uranium system wastes 96% of its fuel, whereas the liquid fuel system is consuming 96%. And this is the difference in footprint that we're seeing. In terms of intermediate level waste and high level waste, we've got a similar profile. So the liquid fuel systems are substantially different. Now this one's interesting. This is nuclear waste. This is what's in nuclear waste. Most of it is uranium-238. If I took a piece of uranium-238 and I bombarded it with neutrons, over time it would become uranium-233. That's actually the fuel isotope for the liquid fuel system. And because liquid fuel doesn't have the shielding problem, we can have particles in that fuel that in a way that everything will interact with everything else eventually. What this means is the liquid fuel system can slowly consume as fuel the spent nuclear fuel stockpile. We now have a solution to actually process and dispose of thoughtfully spent nuclear fuel. Right. Next technology was the burning of iron powder. When we manufacture, we need temperatures up to 2000 degrees in large quantities. How do we do that? Hang on. I'm trying to actually get my, okay. Right. So manufacturing consumes about 54% of our primary energy supply. Like what happens in China? And it's quite concentrated. It's taking a massive chunk of our fossil fuel energy systems. If we were to fossil fuel heat generation, if we were to knock out coal and gas, most of our manufacture would just simply stop. We don't really have a way of actually we haven't really talked about replacing manufacture in terms of, well, if we didn't have coal, how would we do it at the scale and volume we're talking about? These are the temperatures that are required for some tasks. Most of the time we're around 1200 degrees for sustained periods of time. Things like ore smelting and making of cement. Okay, how do we do that? Well, there's lots of ways we could do that, but all we've got that's non-fossil fuel at the moment is either biodiesel, hydrogen, or electric arc resistance. They all work on a small scale, but when you want to scale them up to replace what we do for coal, then we've got a serious bottleneck problem. I'm proposing the following. We take pure iron powder and we combust it. This is the iron powder that's used in the powder coating industry, so it's a mature technology. When they're oxidized, they release chemical energy in an exothermic reaction. It can be up to 2000 degrees Celsius. Once we have that high-end heat, we can support smelting and refining, manufacture, and we can also start producing hydrogen as well. 1 ton of iron powder contains around 1.6 to 1.9 megawatt hours, depending on the final oxidization state. What's interesting is when we burn the powder, it's not destroyed. Pure iron becomes iron oxide, what we call rust. We can reduce that rust either in a hydrogen atmosphere, a syngas atmosphere, or electrochemical reduction system using electricity. We can strip that oxygen out and we're back to pure iron powder. So that fuel can now be recycled. So we go, the group that actually that's commercializing this in a pilot scale, they've recycled their fuel through 5 cycles now. And they've lost about between 3% and 0.3% in each cycle. There's a group called Metalot, again in Copenhagen. They did a proof of concept. This was someone's PhD in 2020, and a prototype unit that's a 100 kilowatt system that was put in a brewery was running. So that is a system that will sit in your living room in terms of size, and it's producing 100 kilowatt hours of thermal energy at 1960 degrees Celsius. So if we have 1 ton of, say, pure iron metal, you put it through you melt it into a liquid and then you atomize it to make the powder. And so you're producing about 1.6 megawatt hours a ton to produce the iron powder. You combust it. So there's very little exhaust plume that comes off this. And we're getting between 1.6 and 1.9 megawatt hours of thermal energy at temperatures that are really high. It's got an energy return on energy invested of approximately 6 to 1. 6 to 1. I'm not sure that's correct. 0.6 to 1.9. Yeah, that's not correct. I think it should be 3 to 1. All right. What's interesting is we can actually put human sewerage through pyrolysis and take the syngas from this to actually reduce and reprocess that iron powder. Take the annual sewerage of 45 average people, put it into a plant to dry it out. This produces 1.1 tons of sewerage solids. Use a thorium molten salt unit to heat, and we are producing a number of products. 35% of the mass goes to gas, and that gas is about half hydrogen, half carbon monoxide. Put that gas, you burn some of that gas to raise the heat to about 800 degrees. And we end up producing, we're taking, say, 1.43 tons of iron oxide powder, and you end up with 1 ton of pure sponge iron, which can then be combusted. So there is a relationship between human sewage and human settlement and recycling and industrial metal fuel. This is very interesting in terms of circular economy outcomes. It takes 23 tons of dried sewage sludge to produce 1 ton of hydrogen, or the annual generated sewage of 877 people. So this is one way of generating hydrogen. Whether it's the sensible way to do it and the most effective way to do it, that's a different question. Next thing, make batteries out of something else. So there are lots of chemistries we could make batteries out of, but at the moment, the entire world is focused on lithium-ion chemistry. This is a chart of the theoretical volumetric density of an atomic isotope potential, theoretical potential. So volumetric gravity density versus gravimetrical energy density. What's interesting, the better the system is, close to the top right-hand corner it is, the worse it is the bottom left-hand corner. Lithium-ion batteries are actually not the best system. There's your sodium-ion batteries there in the purple. The fluoride in your toothpaste can be used to make a battery, and that's your green ellipsoid there. What's interesting is the metals and that we're after are all things like zinc, fluoride, sodium, magnesium, what have you. These are all things that are found in industrial waste, and in particular mining waste. The valuable part becomes processing and refining into something useful rather than the raw materials themselves. The problem is every chemistry I've looked at, this is just the cathode. When you put the whole system together, it still needs copper. It still needs nickel. It still needs graphite. So we still have some of the resource bottlenecks, but at least there's less of them. What this means is there'll be less vehicles on the road, but we will make them out of different chemistries. It's not rocket science, but for some reason, we are reluctant to actually fund research projects that look at this on a proper scale. And the last technology is ammonia-fueled ICE. Ammonia-fueled engines are being developed for maritime shipping. Again, in Copenhagen, the Maersk shipping operation, they've actually got several test engines that have been running now for 6 months continuously. Ammonia can be stored and transported much easier than hydrogen. We know what to do. The technology is mature. The problem is ammonia is toxic to plants and animals at room temperature and pressure. So what this means is it needs to be stored under pressure. The burning of ammonia does produce a series of nitrogen-related exhaust emissions. They tell me there is a catalytic converter system to manage that. Where I see trouble is in an engine that is not tuned properly, we're going to have unburnt ammonia coming out the exhaust. So what that means is, while this is an interesting technology, it's probably not going to be used in concentrations of human population like a city. Toyota has actually brought out a concept engine in a passenger car, an ammonia-fueled passenger car. It's great technology. It tells me it's nice and mature for reasons I was just saying I don't think we will see it in cities. But what it does tell me is the technology is mature enough to be put in a large ship all the way down to a passenger car, which means if we can do that, we can put it in, say, a turboprop engine for an aircraft. Right, so coming to the end, electricity generation, we will take all non-fossil fuel systems and use them to manage volatility until we learn how we actually generate these systems. There will be no buffer for wind and solar. Baseload power generation will use the conventional uranium-fueled light water reactors as a way of maintaining system pressure and to project electricity over a long distance. These systems will produce spent nuclear fuel, and that brings us to the liquid fuel systems. which will use a cocktail of thorium, uranium, and spent nuclear fuel in a molten salt system. Over time, I believe this will become the dominant energy system. What's interesting is we can decentralize the power grid. So every industrial site can have its own power unit sitting in the car park. Every mine site, for example, could have a small power system as part of the circuit, of the process circuit. Transport, well, all the short range stuff that happens in a city, passenger cars and everything, will be a combination of electric vehicles and hydrogen fuel cells that are made from sodium and fluoride battery chemistries. We have to expand the power grid to charge those electric vehicles, though. All our heavy vehicles and long-range vehicles, they're hydrogen fuel cells, but we need to produce the hydrogen. This will work if we can do it, say, using burning iron powder, and if we use seawater. And if we use electrical power to actually recycle and repurpose that iron powder. Now we're back in business. If we can do that, we can actually produce hydrogen in a decentralized fashion. We don't have to store it for very long or in large quantities, and we can use it as we go. Long-range transport is ammonia-fueled ICE, so this maritime shipping, aviation, and intercity rail, especially freight rail, all the diesel locomotives that would actually replace them with ammonia fuel. We've got to produce the ammonia, but first we've got to produce the hydrogen first, and now we're back to burning iron powder and seawater in combination. So if we can do that, and if we do it in a decentralized context, this will work. Now, there are some technical challenges to overcome here, but there are less bottlenecks in front of this technology than there are in many others. Put it all together, the thorium molten salt will generate electricity, which will manage our conventional electricity demand, charge the electric vehicles, which are most of the transport fleet in cities, which will be sodium and fluoride battery chemistry powered. Combustion of iron powder, well, that'll either go to steel production. There's also a system we're looking at in Sweden, where we're actually looking at the production of steel in a hydrogen atmosphere. And it's great and it looks good, but we need hundreds of millions of tons of hydrogen a year to actually make it happen. So we're going to produce hydrogen, and that can run the hydrogen fuel cell fleets. That's all the heavy vehicles. We're also going to make ammonia, and that ammonia will then fuel the internal combustion engine system of all our long-range transport. The thorium molten salt system, through the pyrolysis of human sewage, will look at the recycling of iron powder. So what we've got is the thorium molten salt supports and facilitates the combustion of iron powder. The combustion of iron powder facilitates the production of the hydrogen economy and ammonia-fueled ICE. And these things can overlap and actually are optimized together. The minerals of interest are as follows. In the thorium molten salt system, most of it is stainless steel and nickel. You do have some exotic metals in there, but they're in much smaller quantities, and you've got a 50-year working life. We do need lithium-7, which is going to be a problem to get hold of, fluoride, thorium, a small amount of uranium, and a very small amount of beryllium. We still need copper and aluminium in a decentralized transmission network. Combustion of iron powder, most of it is stainless steel with brass and aluminium fittings. The fuel is iron powder or sponge iron, which can then be repurposed, and a 60-year working life. Ammonia ICE has a profile very similar to our current ICE fleet. It is not clear what the maintenance cycle is, but to me, we're actually looking at the same metals: stainless steel, iron, aluminium, copper, magnesium. Alternative battery chemistries, well, the cathodes are made of things like sodium and fluoride and zinc, but we still need copper, nickel, cobalt, and graphite. So we've still got some of the bottlenecks there, but there's less of them. That tells us we've got to actually simplify our industrial transport system. Technology metals like rare earth elements are still needed, but in much less quantities than the projected green transition. Conclusions. The green transition won't work, but there are alternative solutions. What's proposed here is 4 technologies. There are others. This is like the start of the conversation. So there's more things that can be done here. The materials required are mostly free of resource constraints. The science of most of the technology presented is decades old and is relatively mature. These solutions still require careful planning and frugal management of energy. The complete restructuring of society will be done in a decentralized form, is what I think it will end up happening as we transition to something like this. So we've got multiple black swans coming in. Some of them might be able to help us. So, all right, thank you. And is anyone still there?
Hi, Simon. Thank you so much. Fascinating presentation as always. I think, yeah, we're running a little bit low on time. We have 5 minutes for questions. So if anyone has any burning questions in the audience, we'll take the questions here first, and then we'll go online for some additional questions.
Good morning, Simon. This is Quentin Campbell. I'm originally from Northwest University in South Africa, whose color is purple. And I'm now associated with the University of Queensland, whose color is purple as well. So I think I share your wife's favorite color for some reason. It's quite interesting and strange that I was actually looking at one of your YouTube videos through a large Ausenco, who I think you probably know. He sort of pointed me there as well. And I saw your presentation, or at least a presentation on the purple transition. Fascinating stuff. And first, just a comment. How do we get this narrative out there? Because, the world outside, we have been bombarded by the media and by politicians, and I don't know why, about, put up enough solar and wind and we're going to make coal disappear, sort of thing. We need the narrative that you've got here. That's the sort of narrative we have to get outside, and I don't think the politicians are clever enough to understand it. Now, I mean worldwide, not just a particular country. My question is, do I understand this correctly, that once your purple system, the transition, is in place, there will be zero carbon involved? And the question is, the reason I'm asking that is because this is a transition. Of course, once it runs, it probably looks like that. But to transition from where we are at the moment into that, you mentioned you still need this metal and you need that metal. Copper and aluminium, for example, is not just heat hungry, it's electricity hungry as well. All of that has to come from somewhere. So the cradle to grave, or the total life cycle analysis of implementing your plan, which I think is fascinating. How much more, what would the carbon footprint be for that?
So all I would say there is it would be less, right? A zero carbon footprint, it will be difficult to arrange because our current society is so dependent on carbon-based technologies. It will be a step change less. We probably will still have some sort of waste plume coming off society, but it'll be smaller in nature, and we might have to deal with a different kind of waste plume. Like we might start having unburnt ammonia as the primary problem and not carbon anymore. As for getting the message out there, I've been asked to present and speak the green transition work, which is now in peer review, to many government organizations, and they all sit there like poleaxe tobbits going like, what do we do? The picture of being slapped in the face with a dead fish, that's actually not a bad description of what they seem to be going through. As I'm packing up and leaving, they all ask me, what the hell do they do? And in the beginning, I didn't really have much of an answer. Now I've got the start of an answer, and I just mentioned this in passing on the way out the door, but I point out whatever happens, it's their responsibility. This is going to happen on their watch. You've got to do it, and you've got to deliver. For that reason, they always come back and they ask me to explain myself, and then we have a discussion about the purple transition ideas. But so far, it's between closed doors. My plan is next to actually get this material into peer-reviewed literature. I hope it doesn't take 2.5 years this time.
Great, thanks, Simon. I think we have time for one more question online.
Yeah, Rick, do you want to speak? Oh, hi, Simon. Enjoyed your talk
G'day, Rick.
as always. My question is, one of the things that's actually most worrying out of all this is that no matter which alternative we look at, our big enemy is not so much technology as time. Because even if we were able to identify all the, settle on how much copper we needed, the S&P tells us that if we found the new copper we needed right now, the new deposit would take 18 years to get into production. So I guess my question is around the new technology alternatives that you put forward to address some of those problems. What do you think the timeline would be from now to commercial implementation of any of those technologies against the targets we've set ourselves for decarbonization?
So if we take it seriously, 3 out of those 4 technologies are in advanced commercialization at the moment. What that means is if we push the button, we could deploy them all immediately. The ones that are not in commercialization is the batteries of other chemistries. They're still conceptual, but the other 3, they're ready to go. The problem with the thorium stuff in particular.
But when you say they're ready to go, are they ready to go from the point of view of proof that they work, or from the point of view of existence of a regulatory framework that would allow somebody to permit and build a project?
So there's a factory that's actually producing these reactors, and there's more than one operator that's doing that, right? And so the physical technology, I saw a factory come together that could be operational next year if we really wanted it to be pumping out units. The problem is, as you said, the regulatory framework to get an official license allowed for these things on the ground. That seems to be the holdup, and that's been the holdup for the last 9 years. In terms of if we can get out our own way, we could actually achieve a lot more. Now that we've got 25 years to get this done, like if we want this to be completely decarbonized by 2050, the nature and size of the system we've got at the moment, I don't think it's practical that we're going to get 100% of it done by then. What we could do is, in a triage fashion, bring online mission critical systems, right? In terms of the industrial systems that actually sort of hold together, go for those first, and we might be faced with a situation where the rest just gets shut down. And so the system has a forced contraction. It's all going to be very messy. Time, as you say, is actually the problem. It just means it won't be easy and it won't be clean. It's the simple answer there.
Thank you very much,
Thanks.
Simon. Yeah, unfortunately, we've run out of time now. But for the online questions that we haven't gotten to, please reach out to Simon, and you can discuss that offline. So thanks again, Simon. We really appreciate your talk. So next week we will have Prof. Quentin Campbell from the Northwest University, who's also now been appointed part-time at the Sustainable Minerals Institute, and he will be talking about magnetic cyclones. So I hope to see you all there. Thank you very much.